In this video, I'll show you how to integrate composite functions using the method of U-Substitution. Let's begin by considering how we might integrate the composite function cosine of 2x. Since the antiderivative of cosine is sine, we might guess that the general antiderivative is sine of 2x plus a constant c. However, if we check this answer by differentiating, we'd need to apply the chain rule and would get 2 times cosine of 2x, which does not match the function we were originally integrating. This means that our guess was incorrect, and sine of 2x plus c is not the general antiderivative of cosine of 2x. However, our guess wasn't too far off. We can correct for the extra factor of 2 by changing our initial guess of the antiderivative. Let's try multiplying sine of 2x by 1/2. Now, if we check by computing the derivative of our guess, we use the chain rule and get that the derivative of 1/2 sine of 2x plus c is 1/2 times 2 times cosine of 2x. And 1/2 times 2 equals 1, so we can effectively cancel these terms, which gives us cosine of 2x. And we can see that this is equal to the function that we're integrating. So this means that 1/2 times sine of 2x plus c is the general antiderivative of cosine of 2x. We were able to do this because the argument of this composite function was just 2x. However, our method of guessing and adjusting might not be so straightforward with more complicated composite functions. To understand how we can integrate some types of more complicated functions, we can think about the chain rule. The chain rule says that if f and g are differentiable functions, then the derivative of f of g of x is equal to f prime of g of x times g prime of x. Then we can think about integrating a composite function as doing the chain rule in reverse. Since the derivative of the left side of this equation is equal to the right side of the equation, this tells us that the antiderivative of the right side should be equal to the original function on the left side. That is, if we take the right side of the equation and integrate it, it should be equal to the function on the left side of the equation, plus c. So we can see that doing the chain rule in reverse requires the integrand to be a product of a composite function and the derivative of its argument. We can rewrite this integral to make it look a little more straightforward by defining a variable u to represent the argument. Instead of g of x, we'll write the letter u. So if we rewrite our original integral, we can substitute u for g of x. But now we have a problem. In one part, we're using a u, and in the other we're using x, and these don't match. So we need to find a way to substitute something in terms of u for this g prime of x dx. If we differentiate u with respect to x, since u is really just g of x, then we'll get g prime of x. If we multiply both sides of this equation by dx, then we'll get that du is equal to g prime of x dx, which gives us a way to rewrite the g prime of x dx. So now we can substitute du for g prime of x dx. And let's think about what this does for us. Now, instead of trying to integrate a composite function, we're integrating f prime of u du. And this antiderivative is just f of u plus a constant c. And now if we switch back from u to x, this is equal to f of g of x plus c. So this method gives us a way to integrate a composite function. Let's take a look at our original example. Originally, we had the function cosine of 2x and wanted to integrate this with respect to x. So now we'd rewrite the argument as u. Then we need to find a way to rewrite this dx in terms of u. If we differentiate u with respect to x, we get 2. And then we can rewrite this relationship as dx is equal to 1/2 du. So now we can rewrite our integral. Instead of 2x, we can write u as the argument of the function. And instead of dx, we can write 1/2 du. Since the 1/2 is a constant, we can pull it out of the integral. Now we need to integrate cosine of u du. The antiderivative of cosine of u is sine of u plus a constant c, so this is all equal to 1/2 sine of u plus a constant c. And now we can rewrite this in terms of x by substituting 2x for u to get 1/2 of sine of 2x plus c, which matches what we originally got by guessing. Let's take a look at another slightly more complicated example. Here, we're trying to integrate 3x minus 4 times 3x squared minus 8x plus 6 to the 7th power. Our goal will be to rewrite this as the integral of some f of u du, where f is a function for which we know an antiderivative. Sometimes doing this takes a little bit of guesswork to figure out what the u should be equal to. Let's start by writing u is equal to 3x squared minus 8x plus 6. We've still got that 3x minus 4 and the dx that would need to rewrite in terms of u, so let's see if we can do that. Let's differentiate u with respect to x. This is equal to 6x minus 8, which isn't exactly what we were trying to get. However, if we factor a 2 out of each term, we'll get 2 times 3x minus 4. So if we multiply each side by 1/2 dx, we can rewrite this as 1/2 du is equal to 3x minus 4 dx. So now we'll rewrite our original integral. We have the 3x squared minus 8x plus 6 to the 7th power, and we can substitute u for the argument of this term. Then we also have the 3x minus 4 dx. We can substitute 1/2 du for this term. And now we can pull out the 1/2 outside of the integral to get that this is equal to 1/2 times the integral of u to the 7th du. We know an antiderivative for u to the 7th, so this is just equal to 1/2 times u to the 8th divided by 8 plus a constant c. And finally, we can substitute our original guess for u to get 1/2 times 3x squared minus 8x plus 6 to the 8th power divided by 8 plus the constant c. So now we've seen two examples of this technique called U-Substitution. This technique helps us compute integrals of some functions that initially look complicated. In the technique, we called one of the terms u, differentiated u with respect to x, and used these to rewrite the original integral in terms of a function for which we knew an antiderivative, and then substituted our original function back in. Like with other techniques, U-Substitution takes some practice, but it is useful for expanding our ability to compute integrals.